Okay, so it's time to start. I want to welcome you to a new event in the TUCS Distinguished Lecture Series. Our guest today, David Harel, is a computer scientist with influential contributions to several areas of our field. David Harel has been a faculty member at the Weizmann Institute of Science in Israel since 1980, where he currently holds the William Sussman Professorial Chair. He made several foundational contributions to computer science in computability theory, logics of programs, database theory, and automata theory. He was influential in several other areas, including software and systems engineering, visual languages, layout of diagrams, modeling and analysis of biological systems, and the synthesis of and communication of smell. He is the inventor of the language of state charts that fed into UML and became widely used in software engineering. His original paper on the language of state charts has attracted to date about 8,300 citations. He also has entrepreneurial experience, having co-founded the company iLogics. He devotes part of his time to expository work. He has delivered a lecture series on Israeli radio and has hosted a series of programs on Israeli television. Some of his writing is devoted to a general audience, and for example, he wrote two widely read books, Computers Limited, What They Really Cannot Do, published in 2 editions, and Algorithmics, the Spirit of Computing, published in 4 editions. His contributions have received wide recognition in the international community. The awards he received include the ACM Karlstrom Outstanding Educator Award, the Israel Prize, the ACM Software System Award, the Emmet Prize, and 5 honorary degrees. He is a fellow of the ACM, of the IEEE, and of the AAAS. He is a member of the Academia Europaea and the Israel Academy of Sciences, and he is a foreign member of the US National Academy of Engineering and the American Academy of Arts and Sciences. It's the second time he visits Turku, but the first time in 26 years. And I've been working with David for 2 years now to arrange this event. So without further ado, please welcome David Harel.
Thank you. That was a long list of things you said. So I'm going to deduct it from my time here. But you know what the most impressive thing in that list is? I think one of the academies you mentioned, the American Academy of Arts and Sciences, so I was elected last year. The claim to fame is Al Pacino was also elected the same year. He did not come to the ceremony though. And I went there because my daughter wanted the signature, but he didn't come. So Ian, thanks for inviting me, and as I said to you yesterday, thanks for being persistent. We've been trying to arrange this for 2 years, and so thank you for that. Now, this talk, I asked for a little more than an hour, but only on condition that I get the feeling that people are not falling asleep. I hope I'll keep you interested. It's got many, many things, this talk. There'll be things that are 80 years old, and there'll be things that are 1 year old. I'll also show you some slides from 40 years ago, original slides. And there are some things that are kind of technical, more theoretical. Those who find that a little dizzying, just close your eyes for a few minutes, and there'll be other kinds of things. But I do hope that there'll be something new for everyone. So many people will know many of these things, but I hope there'll be new stuff too. So we're going to be talking about Turing. Oops. Let's get this into... So I'd like to dedicate this talk to Ashok Chandra, who died last year. He was an absolutely brilliant scientist. In my opinion, he spent less time doing science and more time doing science management at IBM and later in other places, which in my opinion was a pity. He could have done even greater things, and also a very close friend, and I'll mention him later on. So, oops. I'm curious, how many people here have seen this movie, The Imitation Game? Okay. So this lecture is not about the movie, and it's actually not even about almost anything that movie is about, but let me say a few words about it. So The Imitation Game concentrates on 2 aspects of Alan Turing's life. One aspect is his indisputed contribution to World War II via breaking or helping break the Enigma system. And the other, of course, is his personal life, homosexuality, and the way he apparently ended his life. Now, these two things, they are exciting and interesting, and they have the ability to make a good movie, just like, I don't know, Amadeus was a good movie, and Shakespeare in Love was a good movie, and these were also movies about great people, but as you know, they do not only concentrate on why that person is great. They, you know, if you make a movie, you have to make a movie. So this lecture, neither of these things will be mentioned, maybe one of them just a little bit, but barely. Instead, what I want to do is I'm going to concentrate on Turing, the absolutely amazing scientist, which of course in the long run is a lot more important than even his contributions to World War II. So I'm going to try to provide a perspective of this past giant scientist through the eyes and work of a present-day person, humble me, who is merely a dwarf in comparison, and the theme of this lecture is going to be the dwarf standing on the shoulders of a giant. So I hope you can see this. There's a little dwarf up there. Oops. So this aphorism, I'm sure many of you have seen or have read or have heard about. If I've seen further, it is because I stand on the shoulders of giants. This is attributed to Isaac Newton. And in fact, Isaac Newton did say this or write this, but he is not the originator of this idea, this aphorism, this picture, this notion. And all I can say is that this thing was around hundreds of years before Newton. And if you don't take anything away from this talk in computer science or in biology or in AI, maybe you should write down the name of this book. It's called On the Shoulders of Giants. It was written in 1965 by Robert K. Merton, who was one of the great social scientists of the 20th century. And it's even got OTSUG is the acronym of the name of the book. It's become kind of a cult book. It's kind of intellectual achievement. It's got hundreds and hundreds of references, but it's a fun book, and it's really like a mystery story where he goes and tries to investigate the origins of exactly this aphorism, and of course he finds that it appeared many generations before Newton. So let's talk a little bit about the giant, about Turing himself. So he was born in 1912, and 2 years ago was the 100th anniversary of his birth, and he died at the age of 42 or so in 1954. The indisputable father or parent of computer science. I would go so far as to say that Turing was almost the Mozart of computing. Like Mozart, he died at a relatively young age and left an incredible, brilliant legacy. And just like with people like Mozart and others who died young, we're left with the tantalizing question of what would Turing have achieved had he lived another 20 or 30 years. So here are some pictures. Turing was also an avid sports person. He ran. And now I have 3 slides in which I will just very briefly give in each slide like a duality of 2 kinds of things that he did which seem almost to be contradictory. So Turing invented computational universality, which is the idea that you can build a computer. Well, he co-invented it. This is also was apparent in the work of von Neumann and others. A computer that can do anything by being programmed. And he conceived of the simplest all-powerful model of computation, for example, Turing machines. But on the other hand, he also worked on the design of the most complex computers of his time, for example, the machine he built to break the Enigma. So here we have simplicity and complexity in one person. He proved that there are many things that computers cannot do, and I think I do not have to explain the exclamation mark here in 1936. Double exclamation mark, because, why is there an exclamation mark here? Because there were no computers in 1936. And yet, Turing and other people around the same time, Gödel, Post, Church, were able to put the absolute limitations on what computers are, will, be able to do even in the future. And this is really maybe the most remarkable thing about Turing's career. But on the other hand, he taught us that there are some amazing things that computers can do. For example, again, breaking the enigma and other things which we'll get to. So that's the other point. So what limitations versus lower bounds versus upper bounds. I don't know how many of you, I'm sure people in computational biology do know this, but pure computer scientists are not always familiar with the fact that he did pioneering work on mathematical and computational modeling of biology. So he was interested in living things in general, but he was also bothered with human issues, and of course you all know that he was concerned with the question of whether computers can think and what does it mean to be of intelligence. And so this is what I really believe, that Turing's legacy and getting to know him will just grow as time goes by, and I think in the far future he'll be recognized not only as the father of computer science, not only as one of the greatest scientists, but maybe even one of the most important and influential thinkers of all time, alongside people like Galileo, Einstein, Newton, Darwin, and maybe Freud and others. And I don't think this is much of an exaggeration. And now to us, everyone else, the dwarves. Many computer scientists feel that much of their research has its root in Turing's work, and I'm one of those people. Not all of our research, but much of our research. And I'm going to spend my time here discussing briefly three of his main lines of work and the crucial way in which they impacted my own research. I will not be discussing state charts or other things that I've been involved in, although there will be a point in which I will ask whether it's not true that Turing predicted state charts or asked for state charts. There'll be a quotation later on, but I won't. So in fact, in terms of my own work, I'll be discussing things that I don't think they're peripheral to my career, but they are not the central things that I've been working on the last few years, but I like them, so I have a good chance here to talk about them too. So here's part one. First the giant and then the dwarf. Part one is about computability. So, as I said, Turing pioneered the notion of what can or cannot be computed, the notion of universal computing, the notion of non-solvability, which is things that computers cannot do, not because we're not rich enough or young enough or smart enough, but because you can prove that they cannot be done. I like saying that proving that something cannot be done by a computer is the same as, so no one, when I'm finished here, 4 o'clock we said, no one is going to go out there and look for triangles which have equal sides but do not have equal angles. But why? No one has ever measured all the triangles in the world. There are infinitely many. But we can prove, we know how to prove that there are no such creatures. In the same way, if you can prove that a problem cannot be solved by any computer, by any algorithm, there's no point in looking for a solution. So this is absolute non-solvability. And in a way, even then in the mid-1930s, he gave the main push to establishing the absolute limits of what can or cannot be computed. And what I'll be doing is I'll be listing 1, 2, or 3 modest follow-ups, which I feel are along the lines of this, and then in some cases I'll get into some details. So I've done work on computability on finite structures, computability on infinite recursive structures, and work on high non-solvability, higher levels of non-solvability, and let me get to some of those. So I'd like to start with this quote from Time magazine. I love this quote. It's from 30 plus years ago. And this is not a quote from a person off the street. This was quoted from the mouth of the editor-in-chief of a certain software magazine. Put the right kind of software into a computer, and the software, the computer with the software, will do whatever you want it to. There may be limits on what you can do with the machines themselves, but there are no limits on what you can do with software. And I was brought up in England by a polite British pair of parents, and they taught me never to say bad words like bullshit. So I will not say bullshit. So I'll just say that this is not true, but it is bullshit. But it's not true, not because this person missed out on a paper, he should have known something he didn't know, he should have read something he didn't read. This person is an absolute ignoramus about his own profession. He has no idea of some of the most fundamental facts about his own profession. It's like someone doing physics who doesn't know about gravity, for example. So, as I said a few minutes ago, some people like to divide the world of computational problems into those you can solve because you have a good enough computer or you're smart enough, and those you cannot solve because you don't or you aren't. And this is not the distinction to make, and along comes Turing and Church and other people at the time, and they make a different distinction between problems that are solvable and decidable if we're talking about binary yes-no problems, and problems that are not solvable, undecidable. And again, you put something up here if you can prove that it does not have a solution. And of course, if you put up this picture, most of you are professional computer scientists, so I don't have to say this, but let me say it nevertheless in case there are people from outside of computer science. A lot of people, when they see this, and they look at this line and they are thinking to themselves two things. They say, first of all, who are you to draw a line there? I have a Lenovo W530. So you might be thinking, he with his W530 cannot solve it. But I, in my backyard, I have a Cray 16. I can solve it. Or this guy who works with, state charts or C++. I have this amazing new graphical, real-time, I don't know what language. Maybe he can't, but I can. Or, he's just dumb and I'm smart and so on. So along comes Church and Turing and other people with, and of course the second question I should have said is, okay, let me first say the following. So the Church-Turing thesis, the way I like to think of it, is not Turing machines can do anything, but all computers, languages, methods are equal. Anything you can do, I can do. Maybe it'll take longer, maybe it'll be harder to do, but anything you can do, I can do, and vice versa, regardless of language, regardless of mechanism, regardless of, given enough resources, time, memory, and so on. And this is absolutely amazing that this fact was established in the mid-1930s. And I should tell you that there isn't a shroud of evidence that this thesis should maybe be changed in the future. And it's called a thesis, not a theorem, because we project it into what will happen in the future. As far as today is concerned, it's a theorem. Everything that we know about today can be proved to be equal to anything else. Even quantum computation does not put a dent in this. The other thing you might be thinking about this line is, okay, Church, Turing, you're standing up here on the table, you're jumping up and down, you're making the case for the robustness of this line, but maybe our friend from Time magazine is right, and there's nothing really here. In principle, everything is down there. And the answer is no. There are so many things up there, including important things, and which I'll discuss. Let me start with a simple example, which I like very much. It's not directly due to Turing, but the proof is based on Turing's work. So let's talk about domino tiling problems. So suppose, what's the main street of Turku? What's the name of the main street? Whatever. So let's say you want to tile your living room and you walk down whatever Arthur said, and you see a tiling shop, and you walk in, and it's kind of strange. There are no tiles with birds and fish and flowers and rainbows. The tiles all look like this. They're divided by the diagonals into quarters. Each quarter is colored with some color. There are various different types, a finite number of kinds, yellow, green, yellow, blue, and so on. And the other strange thing about this shop is that you have to sign a contract if you buy tiles with two clauses. One is not very important, it just makes my life here a little easier. You mustn't turn them around. If he sells you the tile, it has green on the top and blue on the bottom, that's the way you have to use it. This is not very important. The other clause is very important, and that is you have to commit yourself that whenever you tile and you put two tiles side by side, the colors have to match. The touching colors have to match. If you don't like this, 2 blocks down there is the guy who sells the rainbows and the flowers and the fish. You can buy other tiles. Now, the kinds of questions this raises are questions about whether you can tile your living room with the tiles that you find in the shop. There's only a finite number of types of tiles. No problem with quantity. Even if you have a very large living room, he has a supplier who can get lots of tiles, but of the same kind. So let me give you two examples. Here's one example. Let's say the only tiles in the store are these three types. And if I gave you a paper and pencil in a few minutes and asked you if you could tile a large living room, the answer you would find pretty easily is yes. And this is supposed to be a proof by picture. You can see I'm only using tiles of these types. Wherever there is a touching size, the colors are equal. And you can see the periodicity. If you want to do this rigorously, you can prove by induction that this can be expanded in all directions. So actually, you can tile the infinite living room. But let's make a change now. Let's switch the two bottom colors of tiles 2 and 3. And if I ask the same question with a paper and pencil, a few minutes, you would pretty easily be able to convince yourselves that with these three types of tiles, you cannot tile even a very small living room. Quick proof, skip this if it's too quick. Let's say you can. I claim tile number 3 must appear somewhere. If it doesn't appear, then tile 2 appears somewhere, has green over here, so to its left you have to put tile number 3. So you say maybe 3 doesn't appear and 2 doesn't appear either. Only 1 appears, but then 1 has green on top. And above it you have to put number 2, so 2 appears, and therefore 3 appears, so 3. So where does 3 appear? Let's put it somewhere, say over here. Above it we have to put another copy of 3, there's no other possibility. And then because of these 2 greens on their right, we only have the ability to put 2 copies of number 2, then we have a mismatch. End of proof, great. We're not very interested in this particular example or in the previous one, because we are computer scientists. We don't solve puzzles, we do algorithms. And the algorithmic problem is the general problem, which in simple words is, can we mechanize the kinds of considerations we used in the last minute and a half to say yes in the first case and no in the second case? To mechanize it means, can you write a program or build a computer or design a chip, whatever, in any language, in any method you want, which takes as input a finite number of tile type descriptions, 4 times n colors, and all it does is say yes or no. It's a decision problem. Yes, if you can use these tile types to tile any sized area. No, if you can't. And for those who like mathematics, this question, by the way, is equivalent to the question of whether you can tile an infinite living room. One direction is obvious. If you can tile the entire world, infinite world, you can tile any size living room. The other direction is not obvious, but it's true. Does anyone want to throw out why this is true, just briefly? Use Koenig's lemma, if you know what that is. It's a nice little homework assignment. But it's beside the point. Whatever the way you phrase this, it's the same. And this problem is not solvable. No such machine. And again, apart from getting up on this nice table and jumping up and down to make my point, I can't make it sound too dramatic. There is provably no solution to this problem. The tiling problem is undecidable, non-solvable. This kind of problem was discussed by many authors, this particular one by Wang in the 1960s. What Turing did was he dealt with the halting problem, which I hope you're familiar with. Let's go through this quickly, and this was in the mid-1930s. Here's a little algorithm that starts out with some number x. If the number is equal to 1, it stops. Otherwise, it decreases it by 1 and goes back to check. I think it's obvious that this algorithm halts on the number 17. Obviously, it does not halt on minus 17 because you keep going down to minus infinity. It does not halt on 17 and a half because for obvious reasons it skips the 1. It does not halt on pi or on e or on other crazy numbers like those. So I think it's pretty easy to see that the halting set of this algorithm is exactly the set of positive. It doesn't halt on 0 either, by the way. So all the positive integers, that's it. That was easy. Some of these particular cases are not that easy. Here's a slightly less easy one. And let's concentrate here just on the positive integers. How many people are familiar with this? So this is the 3x plus 1 issue. Let's just concentrate on integers here. If it's 1, you stop. If it's even, you divide it by 2. And if it's odd, you multiply it by 3 plus 1. And I always like to ask, does this halt on 2015? we have to work, 2015 times 3 plus 1, blah, blah. The number 7 is a cute number to try this out on. So 7 is odd. It becomes 22, right? Which is even, becomes 11, which becomes 34, which becomes 17, which becomes 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1, bingo. Of course, it halts on all powers of 2 for obvious reasons. So here the question is open as to whether this algorithm halts on all positive integers. This is, in my humble opinion, the most easy to describe open problem in the whole of mathematics. You don't even have to know what a prime number is. Is it true that every positive integer eventually halts if you divide it by 2 if it's even, multiply by 3 plus 1 if it's odd? This has been open since the 1930s, still open, but it's of interest to number theorists. It's not of interest to computer scientists because it's just one example of a program. Well, it's interesting, but we are interested in the general algorithmic problem, which is, just as with tiling, can we solve the halting problem in its general form, which is you're given a program in some pre-agreed upon language, and you're given an input x encoded in some pre-agreed way, and all you want to know is yes or no. How do we run p on x? Would have p halted on x or not? Just say yes or no. And I think everyone in the audience here is sophisticated enough to realize that to simulate p on x is a good idea, but it's not guaranteed to work. Because if you run p on x and you wait, say, for 10 years, and it hasn't halted, and you say, okay, I give up, it's never going to halt, and you go home and you say no, that might be a mistake, because it might have halted in one additional nanosecond or something. But that doesn't prove anything. It just proves that simulation does not solve the problem necessarily. And this is what Turing proved in 1936. There is no such W, the halting problem is undecidable. And this proof was via a very easy diagonalization argument, but at the time it was ingenious, based on the original ideas of Cantor and diagonalization. And if you know what this is about, you know what I mean. But not only halting is undecidable, what else is undecidable about computation? Just throw some examples. Can you tell whether two programs are equivalent? No. Can you tell whether Ian's program for one problem is more or less efficient than my algorithm for the same problem? Can you tell this? No. Is there anything you can tell about computation? No. So here comes, again, in my very humble opinion, the most interesting fact about computability. It's not due to Turing, but the proof, again, builds up on Turing's. And this is Rice's theorem. And if you don't know what Rice's theorem is, then this is the one thing I'd like you to come out of this lecture knowing. Nothing about computation is computable. That was not a typo. Our profession is the quintessential example of the shoekeeper walking around barefoot. We cannot compute anything about computation, anything, except if it's syntactic. Is this program more than 100 lines long? Does this program use the variable x? That's easy. But anything about the functionality, about the behavior of computer programs in general can be proved to be undecidable. I know I should pause a few more seconds for the drama. This is an absolutely sweeping and remarkable result that everyone should be familiar with. So that's the giant and his immediate follow-ups. And now let me tell you a little bit about my own work on computability. The first chapter here is work done with Chandra. So 1979 is almost halfway between Turing's work and today. So Turing's mid-1930s work was 40 years ago. It was 80 years ago. This is almost 40 years ago. So here the homework assignment is to figure out which one is Chandra. And as I said, he very sadly passed away last year. We spent just a year or so together at IBM Research in late 1970s, and we did this work. So I'm going to show you some of the original slides that I prepared for our stock paper in 1979. The paper was titled Computable Queries for Relational Databases. It was couched in relational database framework, but it really is not about databases. It really extends Turing computability, I think, in a very, very natural, and maybe I should say elegant way, from numbers words, which is what Turing machines are about, to general structures such as graphs, databases, hierarchical structures. These ideas and the theorem and the proof have been extended by many people to all kinds of structures. And in fact, this is considered now to be the natural way to talk about computability over structures. So, of course, no PowerPoint then, so I started the talk then by showing a big fat computer with some queries, giving the names of all managers with ID starting 6 and blah, blah, giving the names of all managers whose ID is the Gödel number of a true sentence of first order arithmetic and so on. And then kind of, you don't have to follow all this. I described a general structure which has a domain and maybe some relations. Maybe one of them is a binary relation, so it's a graph. So B is a domain D, finite domain D, with some finite number of relations over that. And then I did the following thing, which I'm going to discuss not on this slide, because this is a little more complicated, but using PowerPoint I can do a better job than this. So, here's a structure. Think of it as a graph. Doesn't make any semantic sense. Points, some of the points are connected by edges, and so on. Now, imagine that we have a function that we want to compute over this graph to give you, as a result, some other graph, if you don't like the word graph structure. And so suppose we have a function that takes that and produces this. Makes sense? Okay, what you do is you raise these from each of the 6 corners, and you get a different structure. Suppose you have another function, and this is okay, there's no problem with this. You can see how to do that. Suppose you have another function that does all kinds of things on all kinds of graphs, and on this particular graph, what it gives as a result is this. This also doesn't seem hard to do. You know that you take the 3 things on the bottom, you erase more stuff, on the top you erase less stuff, and so on. But what does top and bottom mean here? There's nothing in the original graph that distinguishes top from bottom. They don't have names, these nodes. We can turn it around, you know. So intuitively, the point we made in 1979 was that this function is not okay. Doesn't matter what it does on other graphs. But if on this single graph, this is the result it gives, no good. It seems a little slippery to say why it's no good, but let me give you the words. The words that I used to explain why this is not good and we don't want this function around is because it's using information that is not in the original structure. This information might be that you guys prefer the 3 things on top from the 3 things on the bottom. But that information, the distinction, is not present. So you cannot even think of having a function that computes something which doesn't use only the information that it's given, but uses information that it gets from God or from outside. So this function is no good. How do you capture that notion? When you're talking about words or numbers, there's no such thing. You know, a word is a word, a number is a number. You have a Turing machine tape. So, but if we change the original structure a little bit, and we just throw these 3 out, so now this graph has made a distinction between top and bottom, and in this case, a function that gives this as a result will be okay. How do you capture this distinction? And the way we did that was to define a computable query, which is really a computable function over structures, has 2 properties. First, it's partial recursive, which means it's computable by Turing in the standard sense. You can build a Turing machine that you take this graph, you spread it out, or the structure, you spread it out on the Turing machine tape, and you compute, and it gives the result. But there's another constraint, and that is that it's consistent. Later, this was called generic by other authors, and that means, in our definition, preserves isomorphisms. And this is the crucial thing. A function is computable if it's computable in the classical sense, and in addition, it preserves the isomorphisms or the symmetries or the automorphisms, if you want, of the structure. Now you might say, okay, this is nice, you know, this is definitely a constraint you want. I gave you an example, but maybe this is not enough. Maybe there's other stuff that you need. The way to show that it is enough and that this is the right definition is to do what? Is to come up with something like a Turing machine which is complete for this definition and computes exactly the computable. Now you can't take a Turing machine, or actually you can ask, so here's the question that we asked in our paper when we gave this definition, and is there a complete language for the computable queries which would be the analog of Turing machines? So you might be thinking to yourselves, what's the big problem? Just take Turing machines, throw out the ones that are not consistent, that don't preserve isomorphisms. Is that a good idea? It's an excellent idea. Just has one tiny problem, and that is that your programming language, which is now Turing machines that are consistent, has a non-computable syntax. Because by Rice's theorem, you cannot tell anything about computation. In particular, you cannot tell whether this program is generic or consistent. Genericity is the consistency I mentioned, whether it preserves isomorphism. So you can't, that's not the solution. Can you, so the question remains, can you find a language that is, it's a language, you know, you can write a compiler for it. You can tell whether a program is in the language or not, which computes exactly the computable queries, and that's what we did in that paper. And so this is the language. I know it makes a lot of sense. Some things are easy. So language is over relations. You have equality. You can intersect. You can take the complement of a relation relative to the finite domain. And then we have three very strange-looking operations. And we have assignment statements and whiles, loops. And these three operations are kind of curious. I think I have a, yeah, don't read this. I'm just showing you how this was explained in 1979. One operation throws away the leftmost column of a relation, just throws it out. The other adds a column on the right by Cartesian product with the domain. And the third switches the last two columns around if they have two columns. That's it. That's the language. A very simple language, obviously recursive, obviously easy to compile. And so we had one theorem which I won't mention. The main theorem is that this language is complete. It computes exactly and all the computable queries. And as I said, this theorem has been extended and generalized in very natural ways to things much more complicated than just relations. Parts of the proof, more parts of the proof. This is the 4 stages of the main heart of the proof, which is given a computable query, we have to show how to build a program in this language that computes it. And these are the 4 stages, of which the most important one is to figure out how to use this language to compute a relation that represents the set of automorphisms of the input structure. And this is non-trivial, and this is the heart of the proof. And that was the final slide of that talk. I want to mention the second paper that Chandra and I wrote, in which we introduced complexity theory for structures. And we made all the almost obvious definitions, polynomial time, space, log space, over structures. And what I want to show you, this was a year later in 1980. Both of these papers were published a couple of years later in journals. I want to show you the closing slide of the lecture I gave at Fox on the second paper, in which we had some open problems. By that time, 2 of the ones in the paper had been solved, but I want to point you to this one. We asked whether there is an effective enumeration of QP time. QP time is simply the computable functions which are computable in polynomial time. It's the analog of P for unordered structures that, like graphs and trees and stuff like that. An effective enumeration is this set recursively enumerable, or, put in different words, is there an effective language? Is there a language that you can write down with an effective syntax or logic which captures the polynomial time queries? This is obvious for the general case of words and numbers. It's not obvious that you can find even a language for this on these general structures. And this problem is still open after 35 years, and in certain circles, finite model theory, descriptive complexity, it's considered some kind of analog to the PNP problem. It seems like an incredibly difficult problem, and no one really knows whether P time has even an RE syntax. Very briefly, later on with my PhD student Tirza Hirst, we did work on computability over infinite structures. How can you compute over an infinite structure, say an infinite graph? But some infinite structures have finite representations. For example, you have a Turing machine which says whether node I is connected to node J. And we obtain several results, including a completeness result in the style of our 1979 paper for an appropriately restricted class of infinite recursive structures, and more work in several papers on high non-solvability And let me just say briefly what that is. So this is the line we had earlier between the computable functions and the non-computable. So this is Turing's line, if you want, Church Turing's line. But there's been a lot of work, starting with Kleene, by the way, and many other people, about hierarchies of undecidability where problems are even worse. And here I always love to pause and say, especially for people who are not close to theoretical computer science, what the hell can be worse than a problem that cannot be solved? It's a good question. You know, what really can be worse? These two problems cannot be solved. How can I even say that this is worse than that? They're both the worst that is imaginable. And the way to explain that, the way I find it easy to explain to people somewhat outside the field, is suppose that the measure of strength of human beings is hand wrestling. Is that what it's called? And so if we do this, you know, and I push you down, then I'm stronger than you, or vice versa. And suppose that it turns out that all the people in this room are very weak, meaning everyone else out there can wrestle us down. So it's very bad news for this lecture hall, right? But then I add a footnote. David is even weaker. What can be weaker than being weaker than everyone else out there? Yes, it can be worse because I'm even weaker than you guys. You take me down. That's the notion in which two unsolvable problems can be of different unsolvability in the sense that if I have this one for free, imaginary solution, I can solve this one, but not vice versa. And this is called reduction. And I've done a lot of work on this level up here, which is infinitely higher in terms of levels of undecidability from the halting problem, which is down there. So here are some of the problems that I was able to show. So for example, the halting problem is undecidable by Turing, but I was able to show that fair halting, which is the halting problem for concurrent programs where you want it to have a fair computation, that's also undecidable, of course, by Turing, but it's highly undecidable. It's infinitely higher than. So this is, again, a direct continuation of Turing's work. I mentioned the tiling problem. Can you tile any sized living room? And I also mentioned a few minutes ago that tiling the entire infinite space is equivalent to that. But suppose I add a little constraint. See, I'm an obstinate guy, and I want to ask whether these finite sets of tile types can tile the entire infinite plane, but I'd like to know whether this tile occurs infinitely often in the tiling. That doesn't sound like much of an additional restriction, because if you can tile an infinite living room with a finite number of tiles, some of the tiles have to occur infinitely often, right? But I would like to know whether this one occurs infinitely often. That makes the problem not just harder, but infinitely harder. And so this also recurring tiles is of high undecidability. And I just want briefly to say something about Hamiltonian paths. You know that to say whether there is a Hamiltonian cycle or a Hamiltonian path in a finite graph is NP-complete. And I was able to show, let me just skip all this, that detecting Hamiltonian paths in infinite recursive graphs is sigma 1, 1 hard, which is highly undecidable. And I like the proof of this, but I won't have time to get into it. It's got lots of pictures. But it's time I got to chapter 2 of this lecture. 5 o'clock, we said, right? Yeah. Okay. So let me talk a little bit about biological modeling. So Turing was one of the first people who worked on trying to figure out morphogenesis, which is a very broad notion, but he was interested particularly in things that form patterns, stripes, various things like that, when something grows, when a limb grows or an organism grows, and he did work on that. And I've done quite a lot of work on biological modeling using computational methods, but the two projects that I've been involved in, which are, I think, can be thought of as direct modern-day continuations of Turing's approach, are modeling the growth of the pancreas, and more recently, just finished last year, modeling the growth of a cancerous tumor, again as morphogenesis, and I'll try to show you a little bit of those. But first I want to read you this quote from Turing's 1952 paper when he talks about how he thinks biology should be modeled, one proceeds as with a physical theory and defines an entity called the state of the system. One then describes how that state is to be determined from a state at the moment very shortly before. Of course, you can think of a differential equation or a bunch of differential equations as doing essentially this, but one of my beliefs is that differential equations are good for certain levels of biology where you want to model, say, a population and how it grows in a continuous fashion, or how the concentration rises or decreases. But if you want to model something that has actual elements in it that you're interested in, such as cells or molecules, you have to work in a different way and define the state of each of these elements and the combined state of them all. And for me, it's kind of tantalizing to ask whether Turing was searching for a powerful state-based, discrete state-based method for modeling biological systems, and had he be happy with state charts or something like state charts? I don't know. I'd love to think the answer yes. And maybe he would have invented them 20 years before me or something like them. But anyway, I like this quote. Regardless of that, so here's just a little bit about, again, the dwarf on the shoulders of a giant. And the first project I want to show you briefly from 2007, I always, when I do biological modeling, I always work with at least one excellent biologist, because I'm not a biologist, and there's always at least one, sometimes two PhD or postdocs, PhD students or postdocs who work with us. And this is one of the relatively early projects we did, and we use state charts actually to model this. Very briefly, I'll show you how it goes. So the pancreas, so this is done on the data taken from a mouse, but it's the same thing. So you and I, and elephants and mice and others, we all have a gut, which is the pipe that leads essentially from our mouth to our rectum. And in embryonic development, there are several organs that grow from this gut. This is called the gut. One of them is the pancreas, which has two parts. The upper part starts out as a bud, and then it grows and grows, turns into something like a cauliflower. And under the microscope and in papers, people usually use green to color the cells that are pancreatic cells. They are important in insulin construction, and non-pancreatic cells in red. This is a cross-section of the pancreas somewhere between these two stages. Very few non-pancreatic cells, a lot of pancreatic cells that become green over time. Let me just show you a brief pre-recorded demo. While you're looking at this, I don't have time to get into any details. Just take into account that each of these cells is driven by a very complicated state chart. The state chart is written once for a cell. It has probabilities in it and so on. Each of these cells is given the state chart, and the nice thing about this model is we did not put anything in the model that says we would like this thing to grow to look like a cauliflower. All we put in the model were state charts for the cells and a little bit about the blood vessels around it. And the shape of the pancreas emerged, this is what we wanted to try to capture, emerged from the morphogenesis that was modeled here. And again, allow me to say this, I would venture the opinion that Turing would be delighted by this kind of thing. So here's a model, doesn't have a mouse there. You didn't tell the model what the thing was supposed to look like. You just programmed the cells in a state-to-state fashion, and you get something that looks really perfect in terms of its shape. I think we freeze it here. Just hang on a sec with me. Yeah, now take a look up here. We get a cross-section up here. And you can measure the similarity of the cross-sections. You can count the number of green cells, red cells, and so on. And there are a lot of other things you can do. Let me stop this. It just gets a little more elaborate, of course, as it continues. And you can take a look under the microscope, see what these things look like, take a look at the model, see if they look the same number of cells, same shape, and so on. And you can do more, because you're doing in silico modeling. You can ask all kinds of questions, and one thing we asked after this project was ended was, why the hell, excuse me, I'm this polite British guy using why the hell all the time, why the hell does a pancreas grow? Forget about functionality now, we're just interested in the morphogenesis. Why does a pancreas look like a broccoli or a cauliflower, but a lung, which also grows from the gut, from essentially the same kinds of cells, looks like an American football? And, I'm sorry, a liver looks like an American football, and a lung looks even more branching, looks really like a very branching tree. If you take a look at the initial cells from each of these three areas in the gut, you can't tell the difference. Yet one of them looks like this, one of them looks like that, and one of them is a pancreas, and we were able to take our model and play with the density of blood vessels and get this effect. And this hunch was essentially corroborated later on in the laboratory by some colleagues. Very briefly, a cancer tumor. This is a sneak preview because the paper has not been published yet. But to do this work, we started out by thinking of cancer as, you know, a very unfortunate, a very devastating, a very wicked limb. It's like you grow a finger or a tail or a pancreas, but you grow something that's very, very, very nasty. But in terms of what's going on there, we tried to use similar techniques to try to program a cell that turns cancerous and how it operates, and of course the blood vessels, which are very crucial in cancer. And I'll just run this for a while. This took 5 years. It's a very, very complicated piece of work. And I should also mention that in all of these projects that we've done, we made some interesting biological discoveries. No Nobel Prize level discoveries, but someone said to me, when you say that sentence, just put yet at the end. Okay. No Nobel Prize discoveries yet. Well, no one has made Nobel Prize discoveries by modeling computation, except maybe for the work on protein folding. But that was for the technique more than for the results. But anyway, you can see here that we can play with this model. There's lots of things we can play with. But you can also, so these are the blood vessels. They start out just by, you know, cruising along outside. And then as the tumor grows, they start sending their absolutely vicious branches into the tumor and feed it. And I don't know if this demo has it in it, but we can also erase these cells from the screen just to see what the blood vessels look like. Cut it in the middle, see what it looks like, and so on. There's many things you can do here. I don't think this is a very good demo that I chose, but anyway, it's also kind of slow, but I think you get the general idea. And no two runs of these models look exactly the same because there's a lot of probability inside, obviously. As a result of the work that I did with my group and with colleagues on biology, relatively early on, over 10 years ago, I started talking about the need for modeling an entire organism. I call this the whole organism grand challenge, to construct a full, correct, true to all known facts, 4D model of an organism. Not just one cell, not because a cell is easy. There's also been a very interesting piece of work a couple of years ago on modeling a cell, and not because a colony of ants or a herd of elephants or a school of fish is too complicated, but because if you do one fish or one elephant or one worm, you'll get an incredibly powerful view of what life is all about. Of course, the two notions here are in quotation marks full, because this obviously depends on the level of detail you go into. Do you just stick to cells as black boxes and talk about intercommunication, or do you go deeper? And correct is something I'll get to in a few minutes. It'll be the last part of the lecture, which is when do we know that we are done and the biological model is valid. True to all known facts is very, very important. You want to put in your model everything so you want to do an elephant. Say, great, do an elephant, but be sure to take everything people know about elephants and somehow weave it into your model in a consistent way. And then anything that they don't know, and there will always be things we don't know about elephants or worms or flies, you can make up because you're doing in silico biology. I'm not saying that's easy, it's a different story. And 4D because you want it to look good, like these demos in 3 dimensions moving over time. And which particular animal would be a good choice? I like to say here that an elephant is great, but it's not a very good idea, not merely because an elephant is too large, but because an elephant is large in a boring way. So you can find much smaller creatures which have things that elephants have and things that human beings have on a much smaller scale, such as the C. elegans 1091, I think, cell nematode, and they have brains and they have digestive and reproductive systems, and they move and they eat and they read newspapers and they have babies and so on, just like we all do, but they're much smaller. Yet it's a grand challenge. This is not something to be done in 2 or 5 years. This is an incredibly complicated challenge to come up with. And finally, I'd like to talk a little bit about AI. I have not worked on AI per se, but there's a roundabout connection with Turing's work here too. But I'm going to spend a few minutes talking about the Turing Test, not fully aware of the fact that you all know what the Turing Test is, but trying to give it a slightly maybe amusing and different point of view, and then I'll say a word on where I have been able to do a little bit of work too. So Turing pioneered the Imitation Game, which is a Turing test for artificial intelligence. And my modest follow-up of 10 years ago is a Turing-like test for modeling nature, for modeling biology, which I'll discuss right at the end. But first, let's talk about the Turing test. So Dijkstra famously said that asking whether computers can think is like asking whether submarines can swim. I think that's very insightful, because we more or less know what submarines are capable of doing. You know, they go up, they go down, they can move forward, they can fire torpedoes. But you don't say that they swim. You know, this submarine swims very nicely, has a good backstroke. You know, we swim, they don't swim. They float, they submerge, they, you know. And the same, you don't say this computer thinks very well. This computer is amazing at data mining. It does this, it does that. It models stuff, it computes well, but not thinking. Thinking, when people say to me, is a computer ever going to have consciousness, or is it going to think? That's philosophizing. I don't like philosophizing about these things. And when people ask me that question, I always tell the story about Descartes, who, when the story goes, when he was a young boy, he said to his mother, I want to become a mathematician, because then all I'll need is paper, pencil, and a waste paper basket for the errors and the garbage. And then a year later he went back and he said, no, I want to become a philosopher, because I will not need the waste paper basket. So, be that as it may, so this is the Turing test, which I'm sure you're all familiar with. We have a computer, so I claim this W530 Lenovo is intelligent. You put it in a room, you put, say, Ion in another room, and we take this gentleman over here as an, I'm sorry, it's no fun as an interrogator, and you connect the interrogator with the two rooms by wires, because you don't want to smell or to listen, you just want to, and this interrogator can pose questions to the two rooms, and the interrogator has to say where the computer is and where the human being. If they manage to do that, you know, several times in a run and so on, then the computer has failed the test. But if after a certain number of times, certain amount of time, discarding noise and guesses and so on, he is not able to tell the difference, then the computer passes the test. This is, in a nutshell, Turing's imitation game. To give you a feeling for why this is non-trivial, there's been tons of things written about this. The people who oppose this, people who, you know, I don't want to get into that, philosophize about it. I just want to show you that it's an interesting idea and non-trivial. So here are some of the, so imagine yourself the programmer who wants to program a computer to be intelligent. You have to deal with all kinds of stuff. So, for example, let me point to someone. Do you know exact date that Kennedy was assassinated? You don't. I do. Now, does that make me more intelligent than you? No, just means here's a fact that David knows and whatever your name is doesn't know. I'm sure there are 1,000 things that you know that I don't know. Okay. Does anyone play chess pretty well here? Don't be shy. I'll make it easier on you. I play chess very badly. Who plays chess better than me here? Maybe you. So does that make you more intelligent than me? No, you just play chess better than me. So what is intelligence? It's not easy to define this at all. Here are a few. So here's a measure of intelligence. So if we walk down a main street, you gave me the name before, and we take a person at random, not a child, you know, not someone who looks disabled. You take a person, bring them in here with their eyes shut, stand them here in the corner. You tell them we're going to remove this for 5 seconds. Take a good look. Remove this. Guy looks around, we close it, we say, what did you see? Most people will say, first minute I thought maybe this was a cinema, but no, no popcorn. People are more or less all adults. There's someone standing here, so maybe it's a lecture. Doesn't seem to be a big conference, doesn't seem to be a classroom because there are older people here who are not students. Probably a lecture hall, maybe in a university, not a company, there's no people with jackets and ties. You know, all this in 5 seconds. Now, show me the world's most powerful computers connected with the most amazing video cameras, wheel that whole thing into here, let it scan the room for 3 months, and then ask it what you saw. We won't be able to do this. This is intelligence. And many other things like that. So some of these questions, it's easy to decide. So about Kennedy. So we have to decide, you know, are we going to take your kind of knowledge or my kind of knowledge? So each fact you have to decide whether it goes in. You can't have all the knowledge in the world because very fast our interrogator will be able to tell this. There's no person who knows all this stuff. Computation, you have to be careful to take a delay in answering and so on. But then things become more, so describe your parents. So if I describe my father had a little beard. So that's easy, you know, father, immediately beard, you put a little thing in there. But then the next question might be, why did he have a beard? Was he religious? Did your mother like beards? Did he have a skin problem? Did it just match his complexion? You know, and then you have to give an answer to that. How, excuse me, the hell do you do that? And so on. But let me make this even sharper by showing you an imaginary exchange between the interrogator and say the computer or the human. What is a zupchok? And the computer says, I have no idea. So this should be Woody Allen, of course, the interrogator. So she explains, listen carefully, a zupchok is a flying, novel-writing whale. It has been carefully cultivated in a laboratory over several generations to ensure that its fins evolve into wings that enable it to fly. It's also been gradually taught to read and write. It has thorough knowledge of modern literature and has the ability to write publishable mystery stories. How weird. So she says, yeah, that's weird, but do you think they exist? And the computer or the human says, no way, they cannot. And she says, why? Now, if you're a human being, which most of you look as though you are, how would you proceed? Well, I don't know how you would, but I would say something like the following, and maybe you would say something a little different, but something not too. So I would say something like, for many reasons, first of all, our genetic engineering capabilities are far from adequate when it comes to turning fins into rings, not to mention our inability to cause 10-ton ingenious creatures to defy gravity by flapping those things. Secondly, the novel writing part, just, you know, that's crazy. It doesn't even deserve responding. You know, even if you were able to teach it to read and write, you know, writing a story as a whole, don't you have anything more interesting to talk about? You would give maybe a slightly different, but imagine what your computer has to know in order to give this kind of answer. Knowledge about genetic engineering, about literature, about writing, about fins, wings, putting all this together in real time. I have no idea how anyone is able to put together a bunch of knowledge to give this kind. This is not Jeopardy. It's not boom, 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 put 2 and 2 together, which is an amazing feat, by the way, for those who have seen Jeopardy being done by a computer. But this is just so much deeper than that. And I want to end this, just before giving my little 5 cents worth later, by showing you 3 nice conversations that take place 50 years from now between you on one side of a telephone line, a voice on one side of a telephone line, and my answering machine. Now, if you call my answering machine back in my office, unless I forgot to even turn it onto my travel thing, you'll probably hear, hi, this is David Harel, I'm abroad, I'll be back in the office on Thursday the 26th or 17th, whatever. Or if I forgot to do it, hi, this is David Harel, please leave a message after the beep. In 50 years' time, or someone else's, I almost said Turing machine, answering machine, will be able to help you out with lots of stuff. So we're going 50 years ahead, but listen to this. Conversation number 1. The machine says, hello, this is Jim's phone. And the voice says, oh, it's you, listen, this is his boss. I really need to get Jim right away. Can you locate him and have him call me? So the machine says, I'm sorry, Mr. His-boss, Jim is playing golf this afternoon, and he left orders not to be disturbed. While you read this with me, and maybe you chuckle, again, think of programming a machine to deal with these 3 situations better than is done here. So the voice says, he's playing golf, is he? Well, look, I'm thin on patience. This is an American phrase. I'm thin on patience this afternoon. This is his boss calling you idiot, not Mr. His-boss. Get Jim now. So the machine says, I'm pleased to hear that you're spending time with your patients this afternoon, Dr. Thin. Business must be good. If you want to reach Jim's boss, just dial 553-8861. Certainly, you would never find him here in Jim's office. We have him listed in our directory under the alias of the monster. So the voice says, take this message, you son of a chip, and get it straight. Tell him he's not worth the keys on your keyboard. He's fired. Click. Is the volume connected? Because there should have been a click there, an audible click. I don't know. We'll see in a minute because I have something else. Conversation number 2. Hello, I like this one. Hello, this is Jim's phone. Versus, oh, hello, you darling machine. I just wanted to check that we're still on for dinner or whatever. And the machine says, of course, so I have you for Thursday at the usual spot. This is Jim's fiancée, Barbara. Who the hell is Sue? So at this point, of course, the machine is beginning to sweat, cold sweat, trying to get out of the situation. So the machine says, oh, Barbara, I didn't recognize your voice. I've never heard of anyone named Sue. So she says, well, you just said he was meeting with Sue on Thursday, so by this time he's flowing with cold sweat. Oh, that's Sue. Are you sure you have the right number? This is Robert Finch's phone. So desperate attempt to get out of this. And she says, you can't pull that trick on me. Tell Jim it's all over. And a last desperate attempt. You've reached a non-working number. Please check your listing and redial. Click. I think the audio is not connected because it's not making any... should I touch something? Mine is connected, my volume is up, but it's not making any noise. It's usually... Okay. Oh, we'll see in a minute. The third conversation. Hello, this is Jim's phone. And then the voice says, oh, are you satisfied with your present investments? Have you considered the advantages of tax-free municipal bonds? To him, or please give your name and address following the beep. Of course, this is another machine. And then there's a beep. Now, Jim's phone has no idea how to deal with this. Never heard anything like this in its life. So all it can do is say, this is Jim's phone. And the voice says, thank you very much, Mr. Jim's phone. Let me tell you more about our unusual investment opportunities. And of course, this is a conversation between two deaf people, and that's the end of that. In terms of the dwarf on the shoulders of the giant, so I propose the Turing-like test for modeling nature, which I'll describe briefly, and then we'll end. So here's the question that I briefly mentioned about 10 minutes ago. So let's say I have a model of the weather, or of an elephant, or of a pancreas, a whole pancreas, or of a C. elegans. And I'd like to know whether it's okay, whether I'm done. For example, an organism. So in a way, this is the question, because if you're willing to take this grand challenge as one of the things that is worth doing, so other things worth doing in computational biology, of course, are solving problems by building a model around a question, getting an answer, publishing a paper in Science, making a discovery, going on to the next thing. I would like to build a complete model of an organism without starting out with any questions in mind, just to get an understanding, a deep understanding of life. And then the question of what is the criterion for success becomes the important question. Because if you put the challenge up there on the horizon, you have to know when you're approaching it or when you've succeeded. So, as I said, in conventional modeling, you address questions that you have, and you are satisfied with making predictions. And once you've made predictions with your model, the model is valid when the predictions are verified in the lab. Until their predictions are verified, you have to improve your lab work or improve the model, and if you get a match, you've made your discovery. But here, as I said, comprehensive modeling is about understanding the whole thing, not based on any specific questions. And here's the point. You really and truly understand something like this, which is dynamic, if you can build an interactive model that you can play with, which does exactly the real. So imagine that you, an example I love to give, imagine that you've never heard of a bancomat, of an ATM. You keep your money in cash under your mattress. And then you walk down the main streets of Turku, and you see people standing, whatever, see people standing in line, and they do this interesting stuff. They put in a card, they type stuff, they wait, money comes out, they put it in, and you're interested in this. And suppose I allow you to stand there for a month. Take notes. You're not allowed to break the thing open to see what's inside. By the way, inside my ATM there is a little dwarf. This is what I believe. It lights up the pixels. When you push in your card, it pulls it. It looks at it. It very quietly calls the bank. Does this guy have 500 euro in his account? If so, it pushes out the money. You can chuckle, but it's not obvious how to design an experiment that you can carry out without breaking open the ATM to prove me wrong. So unless you can find a way to do that, you must believe me that my theory of a dwarf in the ATM is a valid theory. And I'm not saying this as a joke. This is what I'm talking about here. The question is, how can you tell that you've managed to do that? And my answer is, we want an imitation game. We want to fool an expert. So what we want is the idea of making a prediction and having it being verified in the lab taken to the extreme, in the sense that when I build a model of an elephant or of the weather or of anything in nature, I have no idea what the experts are going to ask me to predict. So I have to be able to make all predictions come true. And for comprehensive modeling, the thing to do is a Turing-like test, but with a twist taken from Karl Popper's philosophy of science. So I am doing philosophy. So we're done when a team of biologists well versed in elephants or worms or pancreases or whatever the subject matter is will not be able to tell the difference between the model and the real thing. So here we have not an elephant, but an elephant laboratory and a model and an expert interrogator, or more realistically, say a C. elegans laboratory. And these things are going to be buffered away from the interrogator, not just by wires, but also you have to buffer away things like this can answer a question in a split second. In a lab it might take 6 months, or it might not be possible. This has to be buffered away by another team of experts. But assume we've done that. And then, of course, if the interrogator can't tell the difference, the model is refuted and has to be changed. And here comes the final point I'd like to make, which is the difference between Turing's test for intelligence and my version for nature, which is the following. Suppose I come to you in a distinguished lecture in 5 years' time with this computer, and I claim this to be intelligent. And Ion and his team subject it to a thorough version of Turing's test, and he says, yes, amazing achievement, your computer is intelligent. Now, he can stamp this computer with a stamp that says, this Lenovo W530, serial number, blah, 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 following software, is intelligent or is a valid theory of intelligence a la Turing's test, and he can stamp that and he can use permanent ink, because the notion of intelligence is not something that's going to change in the foreseeable future. You will learn new things, and I will learn new things, and maybe new skills, but the notion of the fact that both you and I are intelligent human beings is not going to change. But if I come to you with a valid model of a worm or an elephant which passes this test with flying colors, you can stamp it. David's W530 is a valid theory of C. elegans, but do not use permanent ink. The reason is that whereas intelligence will not change, elephants will change. Not elephants, or what we know about them will change. Not only what we know about them will change, this is what we want to happen. We want to improve our knowledge by falsifying theories of other people. So, let me first read what I wrote here. This refutation will happen all the time, even if it does pass the test. Today it will not pass it tomorrow because of the advancement of science. So the test is in the good spirit of Popper, who taught us what experimental science is all about. You come up with a theory, I shoot it down, right? Einstein shot down Newton. Quantum mechanics shot down Einstein. String theory or whatever is shooting down quantum. I mean, it's just major examples, not shooting down, obviously, but you know what I mean. But this is happening all the time. Even your very humble dwarf has had this happen to him. And there was a case in which something in the model that we had of some cells did not work the way the experiments showed. And I had my student program a particular dining philosopher's algorithm into the model as though there were some forks there that had to be lifted to do something. And my biologist colleagues got so angry, they said, but there isn't anything there. And I said, this is the dwarf in the ATM. Works. Does exactly what the experiments show. That's the theory. Now, I knew that there was no fork there. And they knew there was no fork, but I wasn't angry. I wanted to prompt them to do more work. And they did. And 6 months later, they discovered the real reason for what we were trying to capture there, which had nothing to do with forks. There was some cascade of signals that no one knew how it really worked. That was a discovery. And I'm not taking responsibility for the discovery, but I'm taking responsibility for making the biologist sufficiently angry to do the work and figure it out. Just like me believing that there is a dwarf in my Turing machine makes you upset. You don't like it. But go home and find a way to disprove it. I'm not saying there isn't a way. There are ways. It's not trivial. And this is going to happen all the time. So this is a Turing-like test with a twist taken from Popper's philosophy of science. And we need a better buffer, which I already said, for this kind of thing. And just as a final remark, please do not go away from here saying, this guy Eon invited this crazy Middle Eastern computer scientist who told us that he's going to build a model that will pass this Turing test. It's not an easy test, and it might not be realizable at all. But I want to repeat my point. If you're willing to agree with me that some part of computational biology should be tailored towards building a comprehensive model that does not necessarily start from a particular question, then what confirms that this model is correct has to be, there's no other way in sight, has to be something very much like this Turing test. Just like I mean, there have been other proposals than Turing's for intelligence, but his proposal still stands as a very basic idea that imitation, if you can't define it, at least imitate it. And I think a very similar thing happens here at all. This is just a commercial. Wow. And I just, if it's okay, I want to put on a clip we need audio here though, so if it doesn't work now, then this is a clip that maybe you've seen. I've shown it in the past many times, of music being played to animation. The animation and the physics and the light that's done in this animation are so remarkable that it doesn't pass the Turing test because it's not interactive, and the music is played by real physical things, but it's nevertheless very, very impressive, and it's kind of nice to hear. So let me start this. No, so we'll have to take this out and put the... Yeah. Can you hear anything? People have seen this before? Thank you.
Thank you very much. Any questions?
I have actually two questions. The first one was that I couldn't see where the basic beat came in this music. The beat. There was a kind of fixed beat, and I couldn't see anything in the picture that generated the beat, but I did see the melody there.
I think it's the machine that bounces out the balls, but I didn't prepare this, but I'll have to find out.
Okay. So the second question is that when you're working with biologists, so you're a computer scientist and they're a biologist. Now you're not really speaking the same language. How do you communicate? What is the kind of thing that you work around? Are there these kind of schemes, or how do you actually divide the work, biologist, computer science, so that you understand each other?
So that's an excellent question. It's not that we decide to work together and then divide up the. So I think the two processes are interesting. First, finding the right. It's like marriage.
Okay.
I said to someone here in the coffee break, my father, when my parents had their 50th anniversary, he made a speech saying to all the children and grandchildren, marriage is complicated, but let me give you the good news. After 50 years, it starts getting really easy. So finding, exactly as you said, finding a biologist who can understand my language and I can understand their language and vice versa is not easy. But there are such people. But then the real process that occurs is more or less the following. We just start talking, even before we know exactly what we want to model, and it gets exciting within half an hour, because very superficially put, we ask stupid questions. But we ask them because we're systems people, you know. So he says, oh, well, in this system, you know, the following two things happen, then that causes the third thing. And then a few minutes later, I would ask, but you just mentioned this other thing. Is it always the case, or maybe if this other thing in this other situation? He says, oh, no, in that case, it's a different story. There's a paper from 1991 where they showed it. So I say, okay, right. But then what if we do the following? He says, well, that's been done in the laboratory. Here's a Nature paper. But then what they didn't do is, and then the 6th, 7th, or 8th questions, it turns out there's something they're not quite sure about, that was overgeneralized, or there's a gap. And it's not because we're clever, it's just because, you know, you and I, you know, we want to, the answers, we have to write a program. And then the next stage comes when you start to build a little model. We do a lot of state charts, not only state charts, by the way, we do a scenario-based and so on. But you put a few states, and then it works nice, you know, so the cell can be hungry or it can want to split, and then it does something, and then boom, it does something completely crazy, and then we don't understand. And the biologist said, yeah, of course, because you forgot to put in the following, and we add it. 2 days later, we come back with a more elaborate model, we play with it, he says, hey, that's really nice, yeah, this is doing more or less, it's not doing it often enough, maybe change the probability, and then they say, but now let's try to add something. Then we work a month trying to put something in and it grows. So the answer to your question is not clear-cut, it's not they do and we do, a lot of discussion. The best kind of person to do the actual work that I found is a PhD student or 1 or 2 or a postdoc with a background both in computer science and biology. I've had PhD students who came from biology and tried to learn the computer science. I've had PhD students coming from computer science trying to learn the biology. Less successful. It works, but it's less successful. So if any of you are in the stage of trying to find a good career decision as to where to go, I would say biology and computer science. I hesitate to say bioinformatics because I like to think of it as different. Bioinformatics, again, excuse me for being very superficial. Bioinformatics is, they have data. Sequences of A's and C's and G's and T's, rectangles with lots of colored dots. And we have algorithms. They have to figure out stuff from the data, mining the data, finding patterns. We can help them by building algorithms or using algorithms. That's bioinformatics, very superficially. What I'm saying is, not they have data, we have algorithms, they have elephants and tails and hearts and worms and stuff. And we have F-16s and software and chips. We know how to build these things. Let's try to unbuild do reverse engineering. And doing reverse engineering means you have to work together. They understand the subject matter, they know what's going on, we know how to build systems, and then you work. It's not always successful, sometimes very, very hard. One additional PhD thesis that is not finished yet, which we're very happy about, is simply modeling one cycle that goes between muscle, brain, muscle in the whiskers of the rat. And so we now understand something about why when one of the whiskers hits something and it does this pumping movement, the other whiskers which don't hit it at all, they also do a pumping movement. Why? It doesn't hit anything. There isn't a muscle that pulls these. It goes to the brain sends a signal back, and we modeled this and we made a little discovery there. Very complicated. We worked with an expert neurobiologist who was an expert on whiskers.
Just to follow up, so do you see that...
I'm saying this,
yeah.
Just one more sentence, to give you a feeling that this project, which looks so minor and modest, is very complicated. 4 years of a PhD, 3 years of a PhD thesis, and try to go from there to a complete animal. Brain, movement, digestion, reproduction. It's a major, major challenge, this kind of.
Yeah, so do you see that some kind of computational modeling language will emerge as a kind of common ground for both these?
One of our politicians used to answer every question with yes and no. So, yes and no. There will never be a single language. If only for the following fact. We have lots of nice languages to model interactions on the network level. Genetic networks, this gene does that. We use differential equations, we use all kinds of stuff. You will never ever be able to build a model of a complete piece of biology on the level of networks alone. That's like understanding an Airbus 430 or 340 or whatever it is by figuring out all the connections of the wires and which wire sends what signal to which. You have to understand it on levels of detail like we know from computer science and software engineering. So there has to be a higher level. I think state charts is a very nice language for a certain level. We already use state charts mixed with techniques for doing the dynamics lower down, say differential equations or control theory, and maybe however we'll need something more general than that. There won't be a single language, but the question is excellent because there isn't any kind of agreement yet on what is the best lingua franca to, but I know enough to realize that even just the connecting of the levels of detail is a major, major hurdle for us in computer science. Not just because the biologists don't know enough. It's very easy for us to say, oh, they don't know enough, how can we build a model? That's not the only problem.
Other questions?
In last 10 years of research, what would you say, what surprised you most as a computer scientist in a biological research?
You're moving this, so I didn't get the question, sorry.
Okay, in last 10 years of research, what would you say, what surprised you most as a computer scientist in a biological research?
If I can repeat the question.
Yeah.
The question is, in the last decade of research, what impressed you most as a computer scientist working in biology?
A particular piece of work or?
Yeah, suppose that you are working on the cancer or some.
You mean in my own work? What surprised me most? I've talked about my own work enough. I think there are some amazing people doing work in systems biology, not along these lines, not comprehensive, but people who have their own laboratories and who know mathematics and physics and computer science well enough. So just to give you two examples from our own institution, the computational biology people I'm sure are familiar with, Uri Alon and Amar Barkari. These people, I raise my hat to them. They're so sophisticated and so clever, and they're interested in particular things. Why does this phenomenon affect that behavior, and what is the relationship between this gene and they do deep work, which is based on physics and math and computer science. They build models, they have their own laboratories, they do a lot of optical analysis of what they see, and they come up with amazing understandings. And I'm the last person to belittle that. I think it's amazing work, but it's relatively low level, and it looks under the hood at particular parts, and now we understand this. And I would like to use all that somehow to get a larger picture.
Other questions?
So go see the movie. I mean, it's not a bad movie at all, but I think you'll be able to see the difference between what's the name of the actor? I think you'll be able to tell the difference between Cumberbatch and Turing after you see that movie.
So David, thank you once again for a very
Thank you for inviting me.